Okay, so let's start. Welcome everyone to this morning section of probability. Today it is a great pleasure to have here Federico Sao, Mariela Valenzuela, Simone Floriani, and Christian Giardina. And you are gonna listen to 4 great talks regarding stochastic duality for Markov processes. Federico, you can start when you want. And the first talk is going to be about mixing of the averaging process and its discrete dual on finite dimensional geometries.
Can you see?
Yes.
Okay, so I can start. Thank you very much, Chiara, for organizing this and for the invitation. It's an honor to open the session. And so what I'm going to speak about today is based on a joint work with Matteo Quattropani from Rome. And let's see, okay. The main model, the main actor of the talk will be the averaging process. And as I know it, I mean, this definition, I know it from works and lectures by Aldous, and it can be described in a few words as follows. Initially, each agent has some non-negative real valued amount of money, and whenever 2 agents meet, they divide them on equally. So as you can see, the model is, its description is very simple, and we will see it's mathematically interesting, and it has been proposed by Aldous as an interacting particle system for the study of social dynamics. And it has appeared also in a few other mathematical works, in particular as a gossip algorithm in some theoretical computer science literature, and also by Aldous and Anu, and also in a recent work by Chatterjee, Diaconis, Lai, and Zhang. We will talk. We will also see some results from this paper. So more formally, more precisely, we can describe an unfair generalization of this averaging process as follows. So given n sites and vertices, which will represent agents, spatial locations, whatever, and given that we have a nearest neighboring relation weighted by some symmetric conductances, and we will always assume the graph to be connected, also adding on top of assigning to each vertex some weights, some non-negative weights, then the averaging process is a process of mass moving on this finite graph. This mass configuration will be denoted by eta, and will evolve according to the following Markovian dynamics, which is simply goes as follows: of choosing independently, proportionally to the rate cxy, some neighboring sites, and then we distribute the total mass sitting at those 2 edges according to some proportions given by these site weights. So we will redistribute a fraction pi x over pi x plus pi y on the x side, and the rest will be given to the y side.
Fede, sorry, can I ask you to try to close the blue box on the top?
Yes, sorry.
Oh, thanks.
Yeah, better? Yeah. Okay, so a few comments that what we saw by Aldous. The description by Aldous is just a particular case of this, what I just presented, by taking the site weights to be constant. Then it's easy to see that the dynamics is conservative and also scale invariant. Multiplying by a positive constant, all the mass configuration doesn't really change. Therefore, without loss of generalities, all these pi eta will always be normalized to be probability distributions on the vertex set. And then a few comments on the averaging dynamics. The first comment is that it is really a local instantaneous thermalization at sites, neighboring sites. And this allows to relate the averaging process to a huge class of Markovian models of mass, energy, heat, wealth distribution. Among them, the KMP model, Deep Samples, Kax-Walk from statistical physics. mainly. And also this local instantaneous thermalization is what guarantees that in the long run, globally also, there will be convergence of the averaging process to the reference measure pi. However, there is something peculiar about the averaging process compared to the statistical physics model, because these dynamics is intrinsically deterministic, causing the process to be irreversible, in the sense that given a certain mass configuration, as soon as we have a non-trivial update, then that configuration will never be visited again. And then also in the fact that the steady state of the system is singular with respect to the dynamics, because it consists of just a single absorbing point, which is this pi. And so the fact of having such an absorbing point is also, let's say, connected to the fact that this averaging process is also used in the context of opinion exchange dynamics, where this absorbing point is typically the consensus. Speaking about this continuum mass model, we can also introduce a discrete analog, which we can call binomial splitting, which instead of having mass configuration, we have particle configurations, and the Markovian dynamics goes analogously, again choosing sites according to some exponential clock, but this time splitting the total number of particles sitting at the two interested sites according to a binomial distribution. We given parameters, so pi x over pi x plus pi y for the x side, and the rest will be given for the other side y. And note that this definition is completely symmetric. Again, so the dynamics is conservative, and again we have a sort of local instantaneous thermalization phenomenon type of dynamics. And this time, however, the main difference is that this time the limiting steady state, the steady state will be a real steady state, a non-degenerate one, and actually will be also reversible, and will actually be this multinomial type of steady state with parameters k and pi, if we have k particles in the system. Also, what is important for this talk is to recall that, okay, this binomial splitting with only one particle is essentially just a random walk on this graph with a reversible measure given by pi. And the interaction kicks in as soon as we have more than two or more particles. And the interaction is really encoded just in the fact that as soon as one edge rings, then the particles sitting on the two ends of that edge are forced to decide to jump at the same time. As you can imagine, also, I mean, the name of the parallel session is that these two models, the continuum and the discrete one, are related by some duality intertwined relations. And some of them were already mentioned in the original work, let's say, in the original survey by Aldous and Lanoux, but many more others can be hooked up, following, for instance, the instantaneous thermalization approach that can be found, for instance, in Jardinac, Kuchan, and Vafai. However, what is interesting for us for this short talk is to keep in mind that we want to use these two processes to decompose the averaging dynamics in the following sense, that we want to write the averaging, so this eta t at time t, as a sum of two components, a deterministic one, which will be just the deterministic law of a single particle binomial splitting, plus some noise. And this noise, of course, it's such that it allows both eta t and pi t to really belong to this probability simplex. And since eta t will converge, for instance, weakly to pi, then this noise also will vanish as time goes to infinity. And our main goal of our work and also the talk is to carry out a quantitative analysis of the convergence to equilibrium for the averaging compared to the deterministic heat flow. And also this is related to understanding the effect of the noise. And this will be done in Wasserstein type of distances because of this singularity and the degeneracy of the steady state for the averaging, which does not allow to study it, for instance, via the most usual total relation distance. So a first result, important result, which immediately gives a relation between the eta t and the pi t when speaking about convergence to equilibrium is the one appearing in this recent work by Chatterjee, Dekonisla, and Zhang about the cutoff phenomenon of the averaging process on a sequence of growing complete graphs, homogeneous in the sense that all conductances are normalized to be equal to 1, and also the side weights are all the same. And what they show, interesting, is that the worst case L1 versus time distance of the averaging process from equilibrium displays exhibits a cutoff phenomenon at a time scale of 1 over log 2 log n over n, with a certain cutoff window of size square root log n over n. And yeah, and this abrupt type of convergence, which can be seen here by the fact that at least at first order, if this constant here is slightly smaller than 1, then we are arbitrarily far away from equilibrium. If A is arbitrarily bigger than 1, then we are arbitrarily close to equilibrium. This picture for the averaging process conflicts with what is happening for the pi t, for which the L1 mixing occurs gradually and occurs at time scales 1 over n. So here there is a first mismatch observed in this result. So from this example, our consideration was, okay, this growing sequence of complete graphs are the most typical example of infinite dimensional somehow limiting space. So what happens about finite dimensions situations? And so by using the following definition of finite dimensionality, we derived our results. But let's look first at the definition of finite dimensional sequence of graphs. What do we mean by this? We mean that the single particle, so this heat kernel pi t, satisfies a family of Nash inequalities, which is the following. It's not very important the form of it, but the important thing are the assumptions on the parameters involved in this inequality, which is namely, so it's important to observe that D, which plays the role somehow, the dimension will be uniformly bounded as n goes to infinity. And also the second most important assumption that we require is that this Nash time is at most of the order of the relaxation time, where the relaxation time for the single particle is defined as usual as the inverse spectral gap. Why do we need these assumptions? Well, Nash inequalities are surely weaker and typically implied by isoperimetry, heat kernel estimates, weak Poincare and volume growth conditions, etc., etc. But what is important for us is that the Nash inequalities guarantee that the heat kernel density of this one particle system decays on a time scale. It's uniformly bounded. This heat kernel density is uniformly bounded on time scales of the order of this Nash time. You can call it like this. And this will be the key for our result. And examples of sequences of graphs satisfying this definition falling into these categories, there are plenty. For instance, lattice approximations of nice Lipschitz domains in any dimension, large boxes on the supercritical calculation cluster, the N-dog studied by Diaconis and Salovkost, and fractal graphs of finite dimensions, for instance. So our first result in this class is that no cutoff for the averaging process occurs on finite dimensional geometries. And this slide is a bit full, but essentially what it says is that on finite dimensional geometries, the L1 Wasserstein worst case initial condition averaging process mixes at times of the order of relaxation time. And this type of behavior is completely analogous to what happens for the deterministic heat flow. So this is already an example which shows a different behavior to what compared to the complete graph. And note that for this statement, we don't need any type of convergence of the geometries. So we can have a sequence which satisfies asymptotically our assumptions, but they can be very general. A second result, which also it's important, hopefully will be clear at the end of the talk, is to, instead of studying the L1 Wasserstein distance of the averaging process just at order 1, trying to zoom in. So what happens much closer to equilibrium, namely when so try to understand at which time scales the averaging process reaches the equilibrium up to a scale, on a scale of the size of 1 over square root of k, where k is another sequence which will diverge as the system size. And what we can say by adding uniform ellipticity assumption on the reference measure is that cutoff will occur on finite dimensional geometries at this mixing time, which is just Tyrrell over 2 log kappa. And yeah, this is the formal statement, if you want, with a cutoff window of the order of Tyrrell. And this type of picture is exactly the same again as it occurs for the deterministic heat flow. However, for our case of the averaging process, we need to impose a restriction, which is curious restriction somehow, is that this type of cutoff phenomenon can be established, at least with our techniques, only up to order of 1 over n distance from equilibrium. And note that this type of restriction is not present for the deterministic flow. So now I'm going to conclude just giving some very, very quick proof ideas, at least for the upper bound of these two results. I mean, the proofs are pretty similar and at least use the same ingredients, which is essentially estimating the L1 Wasserstein by the L2 Wasserstein by using Jensen. And then this allows us to analyze the mixing of the averaging via the mixing of two particles of the discrete particle system. Then hooking up by tensorization and comparison argument a Nash inequalities, which we assume for one particle, to a Nash inequalities for two particles, and then having a control of the relaxation time for the particle system by proving an aldospectral gap type of identity for the particle system, namely establishing then on all graphs, actually not just finite dimensional, the relaxation time for k particle system equals the relaxation time of just one particle. And okay, the motivation to study cutoff of the averaging process on finite scale is that it allows us to extract immediately a result about the total variation distance worst case cutoff for the binomial splitting with k particles. Again, where this k is the same k that we used in order to zoom in for the averaging process. And okay, just for those interested, I mean, this result is kind of immediate as long as we observe that at least we can prove a multinomial type of intertwining between these two processes. Note that this type of intertwining is not a Poisson intertwining, but it's really a multinomial type of intertwining, and by using also some analogous arguments for multi-species process, essentially multicolored. And this type of multinomial intertwining allows us to immediately obtain an upper bound for the worst case total variation distance for the particle system. Therefore, in conclusion, I mean, the message of everything is that somehow we are able to prove mixing results for the averaging starting from the analysis of a few particle mixing of a few particle system, but also using the averaging process in order to study the mixing of many particle systems. And for this, with this, I stop here and thank you for your attention.
Thank you very much, Federico. So let's see if there are some questions. So in your last slide, the intertwining relation, is it a sort of duality relation?
It's you can really view it as an intertwining relation in the sense that both relations are going forward in time. So.
Okay, and the cutoff time estimate that you show, okay, at the beginning, that was the log n. Was it the same of the cutoff, the mixing time of the exclusion?
This one?
No, the one before. It was n. I think exclusion is n squared log n.
Yeah. This one on the complete graph. On the complete graph, I don't remember whether it is the same of the exclusion. I can tell you for sure that this one is something kind of that rings a bell of some sort of universality going there for this conservative particle system, is that the mixing time for the exclusion is exactly the same also.
The relaxation time times the logarithm.
Relaxation time over 2 time log
okay.
For a system, for a exclusion particle system with k particles.
Okay. Let's see if someone is typing. I don't think so. So, okay, so we can pass to the next speaker. Mario. Mario?
Is it starting?
Yeah.
No, you see it?
So, so our next speaker is Mariala Valenzuela. Is going to talk about high-order fluctuation fields and orthogonal duality polynomials. You can start when you want.
Okay, good morning. I want to thank the organizers, especially Chiara, for the opportunity of being here today, whatever here means, virtually here. Today, I will talk about one of the consequences of combining duality, orthogonality, and the context of scaling limits, in particular fluctuations. This is joint work with Gioia Carinci and Fran Reddick. First, as Newton said, on the shoulders of giants. This work has a lot of inspiration from these two works, which basically relate quadratic fluctuation fields, right? Okay, I will start by giving you some of the background on our particle systems and some notions to later develop our main result. And I will start by showing you some simulations of the kind of dynamics that we are interested in. So basically, we have particles that interact in a way. In these two cases, the interaction is of the attractive type, right? So particles are attracting each other to their sides. And on the video of the right-hand side, I'm exaggerating a bit the interaction so that you can see it, right? Just that. Okay, we are not restricted only to attraction type of interactions. We want to consider a bigger class of interactions. So these classes, these particle systems are usually described in terms of the infinitesimal generator, where eta denotes a configuration of particles on the whole lattice, right, on set D. And the parameter sigma is the one that determines the type of interaction we have. So we have three cases. When sigma is equal to 0, we have no interaction at all. So we can consider particles moving independently to each other. When sigma is equal to -1, so we have exclusion interaction, when this extra parameter alpha that we have here determines the maximum occupancy of the maximum number of particles allowed at a place. And finally, when sigma is equal to 1, we have this type of attraction that we show in the simulations. Okay. Something else, we are restricting our case to PR to be a symmetric finite range, irreducible Markov transition function. So our systems are symmetric. I want to just tell you a bit about what is known about these systems. I mean, the exclusion process is more known, probably. But we have very good knowledge about these systems. We know we have explicit knowledge of the reversible measures. We also know that they enjoy the property of self-duality. I mean, this is the theme of of the session, right? So I'm going to elaborate a little bit more on self-duality later. We also know for some variants of the processes, for some versions of the processes, the hydrodynamic limits of the process and the fluctuations around them, right? So it is important to touch a bit on reversible measures. By detailed balance, we can really verify that these systems have a one parameter family of homogeneous, reversible, ergodic product measures, in which in each of the cases, the marginal are given as follows, right? So we have, for independent random walkers, we have Poisson marginals. For the symmetric inclusion process, we have binomial marginals. And remember, if you put alpha equal to 1, so if you restrict to maximum one particle, we have obviously a Bernoulli distribution. And finally, for the symmetric inclusion process, we have negative binomials. Okay, so probably everybody knows about duality, but let me just touch a bit on that. So this is like a caricature of the context of duality, right? So we have two processes, and with the respective state spaces, right? So we have eta and psi with state space, semigroup, and generator. And the idea is that we have the following situation. We have one process that we call complicated process, whatever complicated means. And we have another process that is a simpler process, a simple process, whatever simple means, right? So usually in our case, complicated will mean that the process has an infinite number of particles, and simpler will mean that it has a finite number of particles. Then duality is just a way to relate two functions by these two processes, by means of a duality of a function that we call the duality function. And the way the duality function connects both processes, it can be seen either in terms of semigroups, as in the first line, or generators, right? You can imagine that it is then convenient. I mean, then it is easier to compute expectations in terms of the simpler process, because we just have a finite number of particles, and then we can, from those computations, deduce things about the more complicated process, the infinite process in our case. So, as we already saw, duality is useful, right? We saw that in the talk of Federico. And basically, we can use it like in this setting. I'm not going to mention a lot of details, but you can compute the scaling limits by reducing to probably a finite number of particles. Usually, in the context of hydrodynamic limits and fluctuations, it's just two computations on 1 and 2 particles. We can also compute correlation inequalities, ergodic properties, verify well-posedness of Martingale problems, analyze non-equilibrium systems. Usually you have like a system with reservoirs in the boundaries, which is dual to a system with absorbing boundaries. And then you can imagine that the second one is easier to analyze. Okay, so for the particle systems that we care about, there is a special type of duality which satisfies 3 properties, right? So the duality is among 2 versions of the same process. And as I told you already, one version is going to have a finite number of particles, and the other one is going to have an infinite number of particles and a finite number of particles. In that case, we refer to it as self-duality. So these also processes have a duality of the form of product form, in which the products are indexed by the position on the lattice. And finally, since we have explicit knowledge of the invariant measures, it makes sense to talk about orthogonality with respect to the inner product given by those reversible measures. So we ask this duality, the self-dualities that this process satisfies can also be considered orthogonal, right? So that this is actually a result of Christian and Chiara. So we have, just going to mention an example of my favorite process of the 3, the SIP. For the SIP process, the type of dualities are related to Meixner polynomials. I have to say that the duality functions themselves are not the Meixner polynomials, but a normalization of them. This normalization is, of course, has to be invariant with respect to the dynamics. And these are the 3 cases, okay? These are the first 3, the duality, Meixner polynomials. What is important here is, I'm just going to remark that the first order polynomial is some sort of eta minus rho, right? That's just important for later. And we have similar orthogonal dualities for independent random walkers and SEP. Okay, now let me just touch on the last thing before going to the main idea. So the density fluctuation field is really the stochastic object, is this guy, this renormalized guy, that is studied to understand fluctuations. Okay, so what are fluctuations? Fluctuations can be considered as the CLT counterpart of the hydrodynamic limits, right? So hydrodynamic limits, we have some sort of convergence to a deterministic object. So in fluctuations, this convergence goes to a stochastic object, which will be actually a distribution value process, xt. And the way we characterize this convergence is this process, this limiting process is in terms of a Martingale problem. And this Martingale problem formally corresponds to the Ornstein-Uhlenberg SPDE, right? Driven by white noise. So this is already known. There are proofs in the literature for SEP and for CPET. There is none, I believe, but it is, it is easy to do, to just follow. And I want to remark one key observation here is that the density fluctuation field, this guy, remember we have eta here, eta minus rho, can really be written in terms of, expressed in terms of the first order duality function, right? So modulo a constant, perhaps, but this is the idea, and then I'm suggesting something here by the upper index 1, right? So we can probably define higher order fields by substituting higher order, if you wish, or duality functions here with more particles. So the k order field will be the one in which we put duality functions with k particles, no? These are just 3 ways to see the same object. Probably the most convenient one is the last one, in which we really have, for each x in set kd, so we will have a configuration with k particles, that's psi of x, no? So let me now tell you some heuristics about our main result. How do we derive it? So morally, the duality function of 2 particles can be seen as a product of 2 one-particle duality functions. I have to say that this first equality fails at the diagonal, but there are, we have already proved in another paper that the contribution from the diagonal is really negligible in this diffusive rescaling in which the fluctuation theorems are taking place. So morally, if we accept as given these two particles duality relation and one as a product of one particle duality relations, we can think of the second order field as some product of the first order field, right? So negliging what happens at the diagonal. And the main idea and what we hope is probably that this relation, the one in the middle, survives in the limit, right? So probably there is some sort of notion of second order field, limiting second order field, and that will satisfy this product for the first order field. This diamond product, we don't say much. We just assume that it's a nice enough product, because remember, we're talking about distribution value processes. But this is just heuristics. What if we assume that the diamond product follows Leibniz's rule of differentiation, right? So if that is the case, we can really compute to get an SPDE for the second order field in terms of the first order field, right? If we do that just by applying this Leibniz rule, we get to this expression, right? Which is, there is a non-linearity here in which you have the white noise multiplied by the first order field. And okay, so these are just formal computations. We would like to give meaning to this, right? And as I mentioned at the beginning, we are inspired by the work of others. And there is already in the literature this paper of Patricia Goncalves and Milton Jara, in which they actually analyze, I'm going to just express here our second order fluctuation field. And Patricia Gonzalez and Milton consider this field that is between brackets, the square brackets at the end. They call it quadratic fluctuation field because it's of some sort of second order, right? So you are negliging the diagonal. They studied this for SEP1, so the diagonal will be 2 particles, and SEP1 doesn't allow to have 2 particles there, so that's correct. And they characterize the limiting process of this field in terms of a Martingale problem, and this Martingale problem is restricted for test functions of tensor product form and symmetric plus, it happens to coincide, I mean, to formally coincide with this SPD, right? So that's the observation, and we have evidence to support that observation, at least for the case of order 2, and hence then we just conjecture the following, right? So we conjecture the following SPD for the kth order field just by iterating Leibniz rule, right? So at the end of the day, we get some sort of dependency on the field of order k minus 1, right? And at least we again we have this nonlinearity here, and this is basically our main result, right? So we formalize, I mean, we make rigorous this formal conjecture by means of a recursive Martingale problem, right? So we have convergence in distribution of these k order fields that we define in terms of duality functions. And it happens that this recursive Martingale problem indeed formally corresponds to this SPD that we have here. Okay, so just a bit of perspectives of what to do next, or how do we see this? The setting, I'm not going to talk about the proofs because of lack of time of how we prove the theorem. But these proofs rely alone on, of course, duality. Thanks to having orthogonality, we can really control the Carré-Duchamp. And because of duality, we can control the drift term, right? So despite of that, we really believe that this work can serve as a guide to look for higher order fluctuation fields on more complicated particle systems. Also, in this paper in which we got inspiration from, they use this Martingale problem, this quadratic fluctuation field to understand the square of the fluctuation field, right? So just by a renormalization procedure. So probably we can do the same for products like x to the 3 times x to the 5 or things like that, right? So these are perspectives, and I think I will stop here.
Thank you very much, Mario. Are there any questions?
Can I ask a question?
Yeah.
Yes.
Mario, thanks for the talk. I was wondering, how far do you think this nice product is from a tensor product of the distribution?
How sorry, I didn't understand.
How close or how far is this diamond product that you suggest? How far is it from a tensor product?
From a tensor product. I don't know if this is an answer, probably, but the way I think about this diamond product is by really mimicking the whole structure that you have in white noise analysis, right? So you have these width products over there, right, in terms of Hermite polynomials, or this structure that comes there. So I'm just assuming that it's the same structure that we have at the discrete level, right? And over there, if you look at Hermite at weak products, then you also have I think it's for Skohorov integrals that this weak product also satisfies Leibniz rule, right? So that's the only possible interpretation that I have with respect to that. Why tensor products? I don't know. And I see that in umbral calculus, it makes sense to define everything with symmetric tensor products like these purely powers. And this class is enough, actually, right? So there are like density arguments to say that this class is enough. I don't know if that's answering your question or.
Yeah, thanks.
Thank you.
Are there any other questions or comment? So, Mario, we have 1 minute, so I just want to ask something. When you say that you prove that the duality, if you have dual particles on the same site, that contribution is something you can neglect, right?
Yes.
I guess this means at the end you just need to explicitly compute the one dual particle duality functions, like the explicit form.
Yeah, you can think of that in a way. What I was saying really is that But somehow you can neglect this lower dimensional parts in which you have like particles being equal, right? Because these parts really don't make sense. We can justify the fact that we can do that by some sort of Boltzmann-Gibbs principle there. But it's really that you can neglect, and basically you can just define these products of one duality, right? So the delta to the k, the dualities with k particles just by powers of k dot one, or products of k particles, sorry.
Yeah. Okay. Yeah. Because then when you go to asymmetric, it's really hard to compute the, I mean, the kth duality function. And then if you just compute one, take the product, it's way easier.
Yes, as long as you are like normalized and summing over all the places, right? So this is a specific form that the fluctuation field has, right?
Yeah. Yeah. Okay. So if there are no more questions, we can go to our next speaker, Simone.
Hello, everybody. Let me share the screen.
Yeah. So this is the last short talk of this parallel section. We have Simone Floriani, who is going to talk about self-duality in the continuum.
Well, thank you very much, Chiara, most of all, for the invitation. I'm very happy to be here to have the opportunity of present this ongoing project, where the aim is to generalize the notion of self-duality in the continuum. So, as Mario did, let me start by recalling what is self-duality. We have a Markov process, and I will denote it by eta t or by xi t, the same Markov process. And this Markov process is said to be self-dual if there exists a function called duality function that goes from the state space of the Markov process times the state space of the Markov process to R, for which this relation in green holds true. So namely, on the left-hand side, we take the expectation starting from a configuration xi, and we evolve the first coordinate of the duality function until time t, and this has to be equal by taking the expectation starting this time from eta and now evolving the second coordinate. And of course, this relation is useful if the function d is a useful observation, a useful function for our Markov process. And the idea is that we would like to take a dual configuration xi that is simpler than the initial configuration eta that we are interested in studying. And then we will consider, orthogonal self-duality, which means that we have also a reversible measure, and our self-duality functions satisfy the following relation in green that can be seen as an orthogonality relation, in the sense that if we take the scalar product with respect to the reversible measure of the Markov process of two duality functions, where we have in the first one psi and in the second one psi prime, the scalar product is zero if psi and psi prime are different. And the example that we have in mind are particle system on a finite set E, or actually on a countable set, so you can think of ZD. In this case, the Markov process eta t is a collection of variables, eta t of x, which tells you the number of particles at each location x at each time t. And to be more concrete, we can think of the system of independent random walkers, where indeed the particles are independent, and the rate of a particle to jump from x to y is given by a symmetric conductance omega xy times a side parameter alpha y. In this case, the reversible measure is in product form and is product of Poisson measures. Another example, this time of an example of interacting particles, is the symmetric inclusion process, where this time the rate of a particle to jump from x to y is given again by the symmetric conductance, but that multiplies alpha y plus eta y, the number of particles at the radial side. So more particles are at the radial side, bigger is this rate, so there is an attractive type of interaction. And in this case, the reversible measure is again in product form, but is a product of negative binomial distribution. And the nice thing is that both these examples are self-dual, and the self-duality function is in product form. So it factorizes over the sides and is product of falling factorial polynomials. And of course, this is a very useful shape of this duality function that allows to studies several properties of interacting particle system like hydrodynamic limits, endpoint correlation. And the nice thing is that we can take the configuration psi to be smaller in the sense that has less number of particles than our original system that can have in principle infinitely many particles. But what is really interesting is indeed that we have falling factorial polynomials. And moreover, both these examples have also orthogonal self-duality in the sense that there exists a self-duality function that for the independent random walkers is in product form of products of Charrier polynomials, which are orthogonal polynomials with respect to the Poisson measure. While for the inclusion process, we have a duality function, which is products of Meixner polynomials, which are orthogonal with respect to the negative binomial distribution. Okay, but now the question is, how can we generalize this notion of self-duality for particles that evolves in the continuum, like on RD? It is clear that this, let's say, shape of having self-duality function in factorized form over the sides does not make sense in the continuum. So it's really a problem of also on how to formulate this relation. And this question was posed to me by my supervisor, Frank Redick from Delft, where we started to currently work on this project 1 year ago. And at the same time, they were working on the same question, the professor Sabine Janssens from Munich, together with their PhD student Stefan Wagner. So we joined our forces to find an answer to this problem. And indeed, actually, the first thing is to find the right setting for describing this self-duality in the continuum. And the right setting is the world of finite point measures. So now we will look at Markov processes whose state space indeed is the set of finite point measures, for instance, on RD. So we have finite sums of delta Dirac over points of RD. Our Markov process will evolve in this space. So at any time, we have a new point measure. And I will denote by E of theta the expectation of our Markov process with respect to the law of our Markov process, starting from the point measure eta. And now that we have this new setting, the question is, how can we formulate a notion of falling factorial polynomial in the continuum? And to do so, we use this new measure, this other measure called the Nth Factorial Measure, which is a well-studied object in the literature of point measure, and is a measure on e to the power n. So think of RD, so RD to the power n, and is defined in this way: is a sum over pairwise distinct indexes between 1 and big M, where big M is the total number of particles of your system. And what you are summing are Dirac deltas over vectors of points, of which points the one that have coordinates I1, IN. So it's the vector of location xi1 until xin. And why this measure is called Nth Factorial Measure? Well, we can see this relation because if we measure the set B to the power n, we get exactly the Nth Factorial term moment of the number eta b. So eta b factorial divided by eta b minus n factorial. So it's now understandable why it has this name. And now, due to this measure, we can define another object, Jn, which takes two input, a function fn that goes from e to the power n to r, and a point measure. And what it gives back is the integral of fn with respect to the Nth Factorial Measure. So this object has to be thought as a falling factorial polynomial in the continuum. So this is, in a way, is what is generalizing the self-duality function of before. And now it makes sense to ask if we can study the expected evolution of this object while evolving the Markov process eta t. So can we find an equality for this expectation at time t that involves not all the evolution of our big M particles, that can be many particles, but only involving the evolution on little m particles? And just to fix a little bit the notation, the names actually, the expectation of the Nth Factorial Measure is called in the literature factorial moment measure. So we will find an answer to this question, but let me first state some assumption. Our Markov process, eta t, has to be conservative. Namely, the number of particles is conserved during the dynamics. So we can also define the semigroup of the n particle dynamics, and it will be denoted by Ptn. The second assumption is that we want our Markov process to be consistent. What does it mean? Suppose that we start at time 0 with big M particles. Then, if we remove initially uniformly at random a particle, and then we evolve the system with one particle less until time t, what we get is in distribution equal to what we get if we first evolve our system with n particle, and then at time t, we remove uniformly at random a particle. Good. Under these two assumptions, we have our first main theorem that indeed can be viewed as a self-duality result, actually is a self-intertwining result to be precise, and it tells you that the expectation with respect to our Markov process of this generalized falling factorial polynomial is equal to the falling factorial polynomial where we have our point measure at time 0, so our Markov process at time 0, but now we evolve the test function fn with respect to the semigroup of little n particles only. So we were managed to study this expectation that of a system that have a big n particles, possibly m very big, via an expectation involving little n particles only. Now the test function fn has to be taken bounded and permutation invariant. Okay, so now we can wonder to which system, to which relevant example the theories apply, and now I will give you some example. The first one is the free Kawasaki dynamics, which generalize the system of independent random walkers in the sense that now the random walks jump on RD, not on a lattice. And the jump kernel is given by a symmetric conductance times the Lebesgue measure. This process, for instance, has been studied in a paper of Condrati, Cunha, Oliveira, Da Silva, Strike in 2009, where they proved the hydrodynamic limit for this process. And they point out that the reversible measure is indeed a distribution of a Poisson point process. But then we can also study interacting particle system on RD. And here we generalized the inclusion process on RD in the sense that now the particles don't jump on a lattice again, but on RD. We have the same interaction of attractive type of before. Indeed, you can see the product of eta dy times eta dx. And then there is the random walk part given by a finite measure alpha times symmetric conductance. We studied here the reversible distribution. And in this case, the reversible distribution is the distribution of a compound Poisson point process called Pascal point process. And actually, to be more precise, we have that the number of particles in a set A, it will be distributed as a negative binomial. And if we take two disjoint sets, then the number of particles of these two disjoint sets will be independent random variables. But then we can also study system of diffusions, like the Brownian gas, which is simple a system of independent Brownian motions. Also in this case, the reversible distribution is the distribution of Poisson point process. And as a final example, we can have also a system of interacting diffusion, namely a system of M-sticky Brownian motion, where the particles are Brownian motions, but where they meet, they will spend a certain amount of time together. I will not give the precise definition of this system, which is quite complicated, but I want to point out some references here. And just to keep in mind, actually, there is a more general structure that tells you that if you have an n-point motion of particles coming from a stochastic flow of kernels, you will have automatically consistency. So this problem is studied in this paper of Lejean and Raymond. Okay, let me now address the second problem, which is how to formulate self-duality with respect to orthogonal polynomial in the continuum. And here I will follow an abstract approach of orthogonalization that comes from this paper of Litvinov from 2003. And the assumption here is that we have again our Markov process, which is consistent and conservative. But now we also assume that there exists a reversible measure for this Markov process. And this reversible measure is actually the distribution of a compound Poisson point process. Nice. Now we can introduce our functionality setting. We denote by L2 the space of L2 function from the space of finite point measure to R with respect to the reversible measure. Then before we have introduced this Jn that generalize the falling factorial polynomials, and now this can be viewed as a function from the space of finite point measure to R. Then I denote by Fn the set of linear combination of these following factorial polynomials until order n, and I take the closure of this space with respect to the measure mu reversible, so in L2. Nice. Then I define Pn as the orthogonal difference between the closure of Fn and the closure of Fn minus 1. So namely, the closure of Fn is the orthogonal sum of Pn and Fn minus 1 closed. So this Pn has to be thought as a set of nth order polynomials. And what we do is now to take our following factorial polynomial and to project it on this space Pn. And we get another polynomial that we may wonder if this is orthogonal or not. Actually, it is orthogonal by construction, and it is what has been done by Litvinov. And this is actually also be proved to be an iterated stochastic integral with respect to certain martingales. Okay, then our result is indeed that also this polynomial is an intertwiner, a self-intertwiner for our dynamics, for our Markovian dynamics, so as you can see here in this line. And moreover, we have also an orthogonality relation in the sense that if we take the scalar product with respect to our reversible measure of In and Im for two different test functions, we will get 0 whenever n is different than m. So then, just to conclude, we studied a bit more in detail this object into example, like for instance in the Brownian gas system. And as you can see here, if we plug in as a test function this tensor product of these joint sets, where morally we are putting D1 particle in the set B1, DL particle in the set BL, what we get is really a product of Charlier polynomials that are the one orthogonal with respect to the Poisson measure. And similarly, in the case of the generalized inclusion process on RD, if we plug in the same test function, we will get a product of Meixner polynomials, which are indeed orthogonal with respect to the negative binomial distribution. And this was a bit what I wanted to tell you, and I conclude with this slide that recaps the two generalized self-duality results. And thank you very much.
Thank you, Simone, for this talk. Are there any questions or comments? So one thing that I wanted to ask, looking at this last slide, so to go from 1 to 2, this procedure that you described is a sort of Gram-Schmidt.
Right.
So, okay. And then, so as you said, you have the orthogonal relation by construction, but then you have to check somehow the duality relation. It was not for granted.
Indeed, indeed. So let's say that to go from 1 to 2, improving the self-duality property, there were two steps. First of all, indeed, using the self-duality with respect to the following factorial polynomial. And the second thing that was one of our contributions was to prove that the Gram-Schmidt procedure was commuting with the semi-power dynamic.
Right.
So, in a way, the orthogonal procedure is something well established in the literature in infinite dimensional analysis. So we just took it from there. What we did is to prove that there was this commutation relation for certain Markov processes. Which one? The conservative and consistent.
So this proof could be also another proof in the discrete setting.
Right.
I see. And okay, probably does it make sense to now in the continuum to create some kind of mechanism to destroy this conservation?
So in a sense that, like, if our approach can be extended a bit also for non-conservative Markov particle systems?
No, in the sense of a boundary in the discrete. Does it make sense to inject or eject particles? Maybe. So
this is actually something that I'm working with Christian Giardina, Frank Reddy, and Gianni Carinci. And okay, there we will not talk about self-duality, but about duality. Our understanding so far is that this machinery work well, at least for a system of independent particles with boundaries. Plus, but the reservoir mechanism has to be, let's say, modeled in a different way with respect to the one that discrete. But there is a paper of Bertini and a co-author that now I don't remember the name, where they generalize, where they study what I call here Brownian gas.
Okay, so we have a question from the audience, from Beatrice Salvatore. She asks if you can also generalize the simple exclusion process.
No, because so you mean in the continuum, right?
Correct. Yeah.
So like the trivial generalization that you could think of not working. So like a generalization that one could think of is like if we maybe, but this is something that I was not able to do. If we put like if you, I don't know, like take your space, you take a partition of your space and you put a fixed maximum number of particles on each set of this partition, but I was not able to do a meaningful construction of this.
Okay, so it's still open, let's say.
Yeah, like the trivial extension will not work. The trivial one in the sense that if you do it as we did for the inclusion process.
Okay.
I heard
Okay.
something for the symmetric exclusion process in the continuum, but sometimes that still I have to investigate a bit.
And inclusion can be generalized, can be considered in the asymmetric version.
So far, we didn't do that, so
Okay.
I have no idea on how to do that.
Okay.
But
Okay, because you have conservation. I don't know if you have consistency.
indeed,
Okay.
But yes, also because for generalizing for the inclusion process, the consistency is really for proving consistency, we really use that you remove uniformly at random a particle. For other systems, like the removal of a particle can be done also not at random, but you can really pick a specific particle, remove it, and you have a stronger form of consistency. So there are systems that here I have not listed that are consistent and fit in this framework, but indeed for the inclusion, the proof of consistency for me was even a bit more hard than other processes. So for the asymmetric version, I imagine that would be even more complicated.
Okay, so if there are no more questions, we can pass to the main talk of this session with Christian.
Yes.
Okay, so this is the last talk of this session. We have Christian Jardinat, who is going to talk about duality of Markov processes and non-equilibrium statistical physics.
Okay, thank you very much. It's very nice to be here, both in this session and in this whole event, which indeed it's very interesting, as a very interesting program. So what I'm going to discuss are some application of duality, the main theme of this session, to the context of non-equilibrium statistical physics. And my talk, I guess, starts from one of the last questions of Chiara for Federico, that is the setting of boundary-driven system. So just to be concrete, let's think, and I'm saying this also for those that are not really into this topic, a very simple system, which is the prototype of a non-equilibrium setup, is the symmetric simple exclusion process that is driven into a non-equilibrium state by the action of reservoir at the boundaries. And those reservoirs, which physically represents infinite systems that are not affected by the system itself, they are modeled with birth and death processes. So particles are injected and removed at the first and last site of a segment of length n. And in the bulk, in the middle of this segment, there are some dynamics. So the simplest instance is the one of exclusion process, where particles essentially would move like independent walker. If not, they are subject to an exclusion constraint, so that I mean, here in the picture, you see all the allowed jumps of this particle. Whenever a particle tries to jump into a site which is already occupied, the jump is suppressed. So this is very well known in this context. It's like the Ising model of non-equilibrium statistical physics. If we think of the Ising model in equilibrium like the prototype model, what I would like to discuss is the distinction between the equilibrium setup and non-equilibrium. So what is precisely meant by this? So I want to distinguish the case where at the boundaries where the action of this creation and annihilation of particle in the end amounts to fixing the density of particles. So this is the expression of the density at the left in terms of alpha and gamma, that are the rates of injection and removal. We are in the setting of continuous time Markov chain. And on the right, similarly, there is a rho right density at the right. So when those two densities are equal, we will say that we are in equilibrium. At variance, when they are different, we are in a non-equilibrium setup, and we want to study the stationary state of this setup. So this we will call non-equilibrium steady state or stationary states. And as I said, this symmetric exclusion process has played a substantial role in understanding non-equilibrium steady states. Because, again, it shares some aspects with the Ising model that is, it is exactly solvable. There is the possibility to compute explicit formulas from which one can start to understand some generic properties. So before I start my discussion, I try here to summarize the message that I would like to bring. By the way, I apologize if some of the people in the audience, I mean, there is some overlap with the seminar that I gave 2 weeks ago, but nonetheless, I try to add something new to that. So here is a summary of the content. In discussing this distinction between equilibrium and non-equilibrium setup, duality plays a key role in the following sense. So whenever there is duality, and we will see the form of duality in this context of a boundary-driven system, it is possible to relate the equilibrium situation to the non-equilibrium one. So what distinguishes them is the fact that at equilibrium there is no current, no flow of particle if the system is symmetric, because the densities are equal. In a non-equilibrium, there will be a current, typically from the density, from the reservoir with higher density to the one with lower density. So if there is duality, this can be put in a direct relation. And furthermore, if the system is also integrable, like it was the case of exclusion process, and we will discuss another example, then this transformation relating equilibrium to non-equilibrium can be written explicitly. And as a consequence, the non-equilibrium steady state can be fully characterized, meaning that we can compute essentially all the moments for this stationary measure. Okay, so yeah, this it's interesting from a probabilistic perspective in view of the properties that are, some of which are known since long time for the non-equilibrium steady states, other emerged more recently. So the root of these properties are long-range correlation that characterize typically non-equilibrium systems. Here you see an instance in the context of the open symmetric exclusion process. So the explicit formula for the covariance shows that indeed, when you look at a macroscopically distinct point, here parameterized by the y, so you multiply by n, you look at the eta is the occupation at those two points, which are macroscopically far apart. Still, there is a correlation which has this form. It's very weak. In the limit, it will go to 0. but it's long-ranged. And similarly for the higher cumulants, where it is conjectured this scaling, and these weak correlation are actually the source of the structure of fluctuation, which then arise in the limit. In particular, at the level of large deviation, when we look, for instance, at the probability of observing a profile of density which is substantially different from the typical one, we will see non-local large deviation function. So in view of this, it's interesting to connect equilibrium to non-equilibrium. And furthermore, from the other perspective of having a model which is exactly solvable, here again, if we think of the exclusion process, I mean, it is very well known that this can be the root of its solvability are that there is an algebraic description of the model, which is provided by the Heisenberg ferromagnet, the quantum spin chain. In practice, the Schrödinger equation of this system can be mapped to the master equation for the exclusion process. And once this reformulation is given, which I will not discuss, those of you that know it will recognize. The other, I mean, it's not really important for what comes. But once you have this, you can start to play with symmetries, and then you understand the solvability of the model. However, as it often happens with integrable systems, they are very delicate, and as soon as you start to change a parameter in the model, the integrability might disappear. So in this class of the Heisenberg ferromagnet, it's only the spin value 1/2, which corresponds to the exclusion process, which is integrable. If you take another spin value, which corresponds in terms of a process to imposing partial exclusion, then it's not integrable anymore. So it's also interesting, the question of looking for other integrable cases. A first attempt will be, for instance, there is a large class of model which is connected to the redistribution models that were discussed by Federico in his first talk, which is the KMP family of processes. They do have an algebraic description which is very similar to the one above, but now this is in the context of the another Lie algebra, which is SU11. And okay, again, I won't discuss this, but as a matter of fact, here none of these processes are integrable. So the question is of finding another one. It's indeed what I will discuss. So that's what I will try to state more with more details. I'm not sure I will have the time to go through all of this, but we will stop when the time is over. So let me introduce the model that indeed a posteriori can be seen to arise from the construction of the integrable systems, that is introducing a transfer matrix and taking the logarithmic derivative of that to produce an Hamiltonian, which then gives rise to a generator of a process. So we did this in the context of non-compact algebras, like the SU11 that I mentioned before, in this paper with Rowan Frasek and Orge Kurchan. The process that arises, which we call the symmetric harmonic process, is defined by this generator. So I denote the process by eta t. The generator has this form. This is the bulk term, and these are the boundaries. So the bulk, here are the transitions that may occur. We remove k particle from site I. Delta I denotes the configuration of a particle at site I. And we put them at site I plus 1 at rate 1/k. Okay, so there is possibility of multiple movement of particle, not just one, but 2, 3, 4, depending on how many there are. And we do this symmetrically from right to left or left to right. And then at the boundaries, we do something similar when we remove particle. Again, at rate 1/k, we remove a particle from side 1 and we simply cancel it from the system. But we also add particles. And this we do with a rate beta to the k divided by k. So it's easy to see that in the continuous time setup, the holding time in a configuration before a jump occurs is an exponential random variable with a parameter which is the sum of this beta divided by k, which produce the log, and the sum of this 1/k through all the sides, which produce the harmonic numbers. So that's the name, explains the name of the model. So sum k from 1 to n 1/k, it's the nth harmonic number. So that's a picture for the dynamic. Each box, it's a site. There are abundantly many particles, and the particles, k particle, jump from one side to the nearest neighbor to the right or to the left with rate 1/k. And at the boundaries, particles are removed and injected. And the distinction between equilibrium and non-equilibrium, again, when the parameters beta or equivalently, it's a one-to-one mapping, the density associated to a beta, which is beta divided by 1 minus beta. If they are equal at the two boundaries, then there is reversibility. The stationary measure, it's actually a reversible measure, and it's a product measure with marginal geometric. In non-equilibrium, it is what we would like to understand. And it can be easily seen that is a non-product law. That's a difference with respect to the standard zero range process where there is only movement of one particle per time. The more general version of the process is obtained by keeping the same structure, but generalizing this rate, which in the simplest version were 1/k, they can be extended to this form involving some gamma function. This is what originates from the integrability construction. You will never guess a form of this rate otherwise, but once you understand that the previous model, it has indeed an algebraic description, then you can extend that construction to a generic spin value, and you will end up with other processes which are exactly solvable, which are defined by these rates, which for spin 1/2 as 1/2 reduce to the one of the simple case. Here we start to see that it starts to appear the d gamma function. Psi is the logarithmic derivative of the gamma function. And the harmonic numbers are generalized to shifted harmonic numbers depending on this parameter s. So again, for s 1/2, this is reduced to 1/k. Good. So this this generalized version of the process will have a reversible measure, which is product of negative binomial. And we would like to study the non-equilibrium setup. These models, the bulk part of these models were already studied in conjunction to the KPZ fluctuations of the density. There was the MADM model of Sasamoto and Wadati, which is defined by this generator where you see you move k particle, but now you have non-symmetric rates. So the rate at which you move particle to the right is different from the one that you move particle to the left, and it depends on this parameter q. It's in terms of q numbers, which are defined here. However, when you take q to 1, they both reduce to 1/k, and therefore it's exactly our process in the bulk. And similarly, there was the Q1 model studied by Popolowski and then Barakan and Corwin, which again is of the similar structure. You see the rate gets more and more complicated, but not really nothing really substantially different, meaning that there are a generalized Pochhammer symbol in the asymmetric context, which in the symmetric limit Q2-1 will reduce to the function phi that I gave before. That's a picture which explains this limit, and in particular it points to the fact that there is this algebraic description behind those processes. Now, what are the type of results that we obtain by the simplification of duality, and what is the simplification of duality that occurs in this non-equilibrium setup? So the definition of duality, I guess I can skip at this point. My notation is eta for the original process and psi for the dual process. In my case, being a Markov chain in the end on countable sets, the duality relation is actually a relation between matrices. LD is DL dual transposed. This also follows immediate from the action of the generator on the first variable eta, which is so described, being equal to the action of the dual generator on the other variable psi, which is so described. So if you look at this relation element by element, then it's this matrix relation. LD is DL dual transposed. The triangle also already appeared, and it summarizes one of the bottom line ideas of the algebraic approach to duality. That is, duality can be seen as a change of representation of an underlying Lie algebra. In particular, there is an abstract object which lives in the universal enveloping algebra of the Lie algebra. And when you look at two different representations, you get two generators from this abstract object. If the representation are such that these operator that you obtain correspond are Markov generator, I mean that you can associate to them a process. And the duality function between the two processes corresponds to the intertwiner between these two representations. The approach is constructive. I mean, the use of symmetries, as I said, it's very important, as it was already noticed by Gunther Schutz for the symmetric and asymmetric exclusion process again. And yeah, it can be a constructive approach. That is, you take an algebra and you run this construction to get a dual process. Now, to state the results, I also recall the definition of factorial moment, which also appeared in the previous talk. So for a measure, they are this expectation. And I want to recall that in the context of integer valued random variable, an inversion formula is always available if those factorial moments are well behaved. That is, from them, you can reconstruct the measure from knowing all the factorial moments. And in our case, actually, I will use a slightly different definition, which is just a rescaling of the standard one, because of this ascending factorial here in the denominator, 2s, 2s plus 1, and so on. And the reason to do this is that at equilibrium, when we look at the setup with equal densities at the right and at the left, we get a product measure with negative binomial, and therefore these scaled factorial moments are just rho, the density imposed by the reservoir, to the number psi, which is the index of the factorial moments that you look, and then you take the product over all the sides. That's an elementary immediate computation. Now, what is the form that is, so that's a structural property. The dual process in this setup of boundary-driven system, it's simple, not only because it contains just a few particles, but also because it becomes an absorbing process. So these few particles in the long time limit will be absorbed at two extra sites, which here are denoted by 0 and n+1. So the generator of the dual dynamics then takes this form in our case. And in the bulk, the system is self-dual. This generator for the dual process is exactly the one that we started from. And at the bulk, we keep the same structure. You see, we move k particle with a rate phi, here it should be phi s, like before, sorry, I forgot the s. And when we are at site 1, when we act with this piece of the generator, we take k particle and we put them at 0, where they will remain forever. And similarly, from n to n+1. So this, again, the first instance was in the context of exclusion, and then there was the KMP, Kipnis-Markov and Prosciutti model, and several others. It's a structural property of the dual being absorbing for a boundary-driven system with duality. Now, for our process, therefore, we will be in this context. We only have to state precisely what the duality function is in the bulk. And again, it will be these factorial moments properly scaled. So that's the precise statement. The open process, symmetric harmonic process, and this absorbing dual that I just described, they are dual on this duality function, where it appears the density at the left and at the right. So they are connected by this relation. Now, if you take the limit t to infinity here, and you can pass the limit under the expectation, you see that you get a big simplification, because so suppose that you start, so that's the second statement. Suppose that you start with an initial dual particle configuration, which I call here psi check, which is so made, no particle at the extra sites and a certain number of particles in the bulk. Then this function, so this term disappear because you don't have particle, and this is the expectation of this, it's nothing but the factorial moments. And when you take the limit t to infinity here, you will get the factorial moment in the unique stationary measure of the system. Now you go to the right-hand side, you take the limit t to infinity, this psi is absorbing, the dual is absorbing. So in the very long time limit, all the particles will be either at site 0 or at site n+1. So now it's the bulk part which disappear. And at the boundary, you will have a random number of particles at site 0 and the random number, the remaining one of those that you started from at the other side. So therefore, the factorial moments are explicitly given by this polynomial in the rows, row left and row right, where the coefficient are the absorption probabilities. So if you start with psi absolute value particles, the kth coefficient is the probability that k particles are absorbed at 0 eventually, and the remaining one at n+1. So the whole issue is to compute these absorption probabilities. Now that's what we did with Rowan in the paper that we posted a few days ago. You get explicit expression by computing this absorption probability that you can do because the system is integrable. I will comment on this in a moment. That's the result that we get. As you see, it's pretty simple and it's fully explicit. There are some combinatorial terms. It's expressed in terms of partitions and or Young tableau, and it's this rational function which are pretty simple. They become even more simple and more explicit when we change base, if you wish. So rather than representing the process with the occupation number, we describe the dual process by specifying the position of the dual particle, and we require them to be ordered. Okay. Then when we go to this coordinate, the position of the particle description, the factorial moments take this form. So you see, it's this sum again over different indices, and then it's a product here of this simple rational function. So knowing the moments, all the moments explicitly, we can reconstruct the measure. And furthermore, I mean, that should come even before than stating what the moments are. Just as a mere consequence of duality, I mean, independently of the fact that you can really compute this absorption probability, the existence of the dual implies that there is a mapping, which is in the end a conjugation in this setup of countable state space between the original process. Here I moved to the Hamiltonian, which is the transpose of the generator, but nothing is lost, of course. So there exists this relation, which is a similarity transformation between the original process with generator L or Hamiltonian H, which is L transpose, and the generator of the equilibrium process, the one with equal parameters at the two boundaries. So this relation, I mean, we will see, that's the only thing that I will try to argue in the remaining 10 minutes. This P, which we can write explicitly because of integrability, it's the microscopic analogous of what was already noticed by Tailleur, Kuchan, and Lecomte. So in the macroscopic analysis of large deviation in the context of macroscopic fluctuation theory. So here they solve the problem, the variational problem, which arises when you study the fluctuation of the density from its typical value via a complicated variational problem that they could solve by means of a sequence of transformation, bringing this variational problem to the equilibrium setup where the solution is instead well known. So they remarked that this sequence of transformation that were done originally by Bertini, De Sole, Gabrielli, Ionadasini, and Landim, they amount indeed to a mapping from an equilibrium to equilibrium. And the fact that you were changing from equilibrium to the non-equilibrium is then, I mean, finds a signature in the fact that the larger deviation function that was computed here was non-local. Here, at the microscopic level, we will find the signature of the non-equilibrium in the fact that this matrix P is non-local. Okay. Before discussing this, let me just very quickly go through a few immediate consequences of the exact solution. So first of all, it's direct to obtain local equilibrium. So this is something that usually it requires substantial amount of work. In particular, you go via coupling to show that essentially you can factorize the absorption probability like if you add independent particle when you look at the macroscopic scale. And this you do via coupling. Here we have the explicit expression, and therefore we can just check by explicit computation that local equilibrium hold in this sense. So macroscopically, the measure, it's essentially a product measure around each macroscopic point where we will see the value corresponding to the average profile. So U, it's a macroscopic variable between 0 and 1. And Fick law, which relates the current to the gradient of this profile, also follows. Okay, as I was saying, the proof, it's just immediate because we have to show that the moments are the one of the negative binomial. That is, we have to show that this is true when we shift the position by the same macroscopic quantity. Well, if we go to the explicit expression here, we see it immediately, no? Because the x are shifted by n. So in this ratio, what it remains in the limit is simply a 1 minus u, you see, because this is negligible, and this just gives 1 minus u, which is this. And then there is this n, which is the power n, because there was a product. And then there is this factorial, these combinatorial terms coming from the sum. And so it's very simple. And then you need to take the binomial sum and you reconstruct what you want. True. So at micro, we see this local equilibrium. Macro, sorry. When we go to micro, we see the effect of long-range correlation. So we can be explicit for the profile, which of course interpolates linearly between left and right. About the covariance, that's the explicit form that we get. Curiously, but not so much. Well, yes, still curiously, but we will get some flavor of why it's in the end. So when we go to the algebraic description, we get the same expression of the exclusion with a change of sign. So in exclusion, the covariance was negative because the particles, they were repelling each other. Here it's positive. The macroscopic form, it's the same. It's this inverse Laplacian in the interval 0, 1. If you take free dual particles, you get the third order cumulants, and again, it can be fully explicit, and you verify the fact that again, now the third common cumulant scales like 1 over n squared, and you have full control also of the coefficient. So it was proved by orthogonal duality, this form, this proportionality to the difference of the parameter to the n, for the nth cumulant. In integrable system, with this conjecture to have some generality can be checked at the level also of the f, and then the level of the scaling for the nth cumulant. And these weak correlation indeed are there, and as I was mentioning at the beginning, are responsible for the fluctuation that are substantially different from the one if you had simply a product measure describing the local equilibrium. So if you already look at the mass, which is stationarity in the system, you will see that when you look at the fluctuation of this mass, that is the sum of the covariance, that it's different from the one of a product measure by this correcting factor, which again, when you put S equal to -1/2, which is just a formal substitution, because in our case, if you put S equal to -1/2, you don't get the process. But if you do, you will recover the expression for the SEP. Now, why there is this neighboring with SEP arise also from the algebraic description. So I will browse through this because I won't have time to discuss. I have to stop in 5 minutes, am I correct?
It's correct.
Okay. So the point is to realize that indeed, as I said from the very beginning, we are dealing with matrices. So we can describe the generator by combining matrices which indeed form a Lie algebra. So, or better, a representation of a Lie algebra, because Lie algebra is a more abstract notion, and we are looking at the representation in terms of infinite dimensional matrices, which are explicitly written here. So they are called S plus, S minus, and S0. They are the generator of the non-compact SU11 or SL2 Lie algebra. So S0 is the simpler one, is the diagonal. It counts essentially how many particles there are on each side. S plus and S minus, they are respectively a lower and upper diagonal. And the state with one particle, with n particle at site I, it will be described by this vector. And therefore, the representation is defined by specifying the action of these matrices on this vector for all n, and it's given here. So this ket, it's just a notation for the orthonormal vector, the standard orthonormal vector. Okay, now it is known in the physics literature, especially from high energy physics, that the Hamiltonian that I associated to the process can be indeed described in terms of the psi function, the gamma function, acting on this Casimir operator associated to the algebra, for those of you that knows this from the algebra theory. And our contribution in this paper with Rowan and Jorge was to notice that it is possible to define boundary terms, which are also algebraically described like this, which indeed defines the process. And the process remains integrable with this boundary. That's a non-trivial issue, because if you take a generic integrable model and you start to add boundary terms, usually you break the integrability, unless you really respect the structure which is imposed by integrability. And in actually obtaining our results in the more recent paper with Rowan, for us it was crucial to observe that in the bulk, this is an expression which is rather involved, because in principle, I mean, if you want to get something explicit, you need to invert the basic operator are these S0, S plus, and S minus. Here you combine them into this, I don't know how it's called, BB, math BB operator, and then you put it into the gamma function. So it's very much implicit, but it's not really needed. There is an explicit representation for the Hamiltonian in the bulk, which we realized, and it's just given here in this form. So there is this term describing the jumps to the right, and this term describing the jumps to the left. And once you have this, the duality, it's indeed an instance of the change of representation that I alluded at the beginning. So I will not show the computation, but I will just flash the slide. So that's the boundary generator. Look at the blue part. So the statement is the following. There are two representations for the site 0. The one that we have been discussing so far with the continuous, with the infinite dimensional matrices. And then there is this other representation for S plus, S minus, and S0 in terms of differential operator. And the intertwiner between these two is known, and this is what is written here. Now, this abstract object in this representation becomes the dual, and in the original representation, in the representation here on the left involving the rows, it's the original boundary generator. So you get this expression, and by intertwiner, you get the duality. If you want, I'm happy to discuss this. For the mapping between equilibrium and non-equilibrium, the remark again, it's once you have the algebraic description, you can make, so that's the boundary term. In the bulk, the system is symmetric with respect to the total creation and annihilation operator. In the bulk, you can make a local transformation which removes this first, with this, the rotation with S minus. But then you have this S plus, which at the left and at the right, they come with different parameters. So if you want to remove them, you will have to act non-locally. And however, when you do the first step, the local one, when you remove this, so this is what is done here in H prime, you see that you get something which is upper triangular because it contains only S0 and S plus. And therefore, the spectrum of these is not different from the one where you conserve only the diagonal. This is well known in algebra. If you add an upper diagonal matrices, you will not change the spectrum. And therefore, these Hamiltonians, they must be connected via similarity transformation if they have the same spectrum. And in particular, both equilibrium and non-equilibrium can be connected to this one, and therefore a relation between them can be established. Okay, I will stop here and I will jump to the summary slide where again there is sort of summary with a list of some open problem. Thank you very much.
Thank you, Christian, for this nice talk. Are there any questions or comments from the audience or from the other speakers?
I have a couple of questions, if possible.
Yeah, go Federico.
Yeah, thank you, Christian, for the nice talk. I was wondering whether when you write down the HIs with these exponentials, whether you can hook up something analogous also for SU2. Would that correspond to some exclusion, like
partial exclusion?
So indeed, this construction involving the psi function, it's the same in the compact setup of the SU2 algebra. And if you specialize to spin 1/2, I mean, first of all, 2 remarks. In the compact setup, this series define the psi gamma function, they just become sum, they truncate for sum. So for spin 1/2, they will have only 2 terms, 0 and 1. And if you specialize this construction to that context, you will recover exclusion. However, as I said at the beginning, spin 1/2 is special for the compact setup. If you take spin 1, you will get an Hamiltonian with a constant, a term proportional to the coproduct or the scalar product, Si, Sj, and then the square of this. And as a matter of fact, in this representation that we use, that Hamiltonian is not stochastic because the rates out of the diagonal are negative. Now, this does not exclude that in some other base it is, but because the true value of a matrix depends on the base that you choose to look at it. But the standard one, it is not stochastic. Yeah.
Fede, you have another question. Then there is one from Patrick Ferrari in the audience. Go ahead.
Yeah. So the other one is quicker. Do you think that, do you know whether this harmonic model is somehow can be viewed as a local thermalization or something else, since particles are moving more than once at a time?
Exactly. So I confess that this question it's on the air, and I confess that I didn't have time, although I wished to seriously think about it. The difference with respect to the standard setup is that we already start from something where you allow for multiple movement. So it's not really clear if what we will get by the instantaneous thermalization will correspond to, again, the redistribution model of the SU11 algebra, like the redistribution model of KMP, or something else. I didn't look at this yet, but it's an interesting question to look at, I think.
Okay, so Patrick is asking if the expression you obtain using duality, to what large system asymptotic can be used for?
Yeah, so the first simple application, asymptotic application, is the one described here for the statement of local equilibrium. Then, of course, it is in the, next, what we would like to do next is to describe macroscopically, and therefore via some asymptotic limit, fluctuation, I mean typical fluctuation, and large deviation. So what I would like to do next is to, reobtain. Well, first of all, for this system, it has not been done to what is the large deviation function for the density, but this should be obtained as a scaling limit of this non-local transformation that is associated to duality. So this is, the application that we have in mind, but we didn't do yet.
Okay. Let's see if there are any more questions or comments. Christian, I have a quick question. In the slide where you have the two representation, the continuous one and the discrete one. So the continuous one, you get a diffusion. There is which is exactly both solvable.
Okay, so you are pointing again to another to-do chapter of this, which I can summarize in this slide. So that's the generator of the process that you would obtain when you look at that abstract Hamiltonian in this other representation. It's a Lévy process because there are jumps. It's not a diffusion. There are derivative of all order, not just first and second order derivative. But indeed, it has the integrable structure in it by construction. So lots can be done on this process.
Yeah. Okay. So if there are no more questions, let me really thank the speaker of this session again. It was very nice seeing you all. And let me also advertise next talk in 10 minutes from it's a plenary talk from Marcelo Viana from IMPA. Okay. Enjoy the conference.
Thank you, Chiara.
Thank you. Bye.
Thank you so much. Bye-bye.
Bye.